Okay, so here's part two of the quantum physics of matter practice final exam. So picking up here with number 7, a system of non-interacting electrons is confined to a volume V. Part A, derive the Fermi energy at zero temperature. Part B, compute the total ground state energy. Part C, derive the degeneracy pressure. Part D, explain qualitatively how electron degeneracy pressure stabilizes white dwarf stars. So we'll go through A through D in a condensed manner, and then I'll go over the derivation of part A more in detail on the second page. So Fermi gas and degeneracy pressure for electrons with spin degeneracy 2, n equals 2 times the quantity V over 2 pi quantity raised to the third times 4 pi k sub f cubed over 3. So k sub f equals 3 pi squared n to the 1/3, where n equals capital N over V. The Fermi energy is E sub f equals h bar squared over 2m times 3 pi squared n to the 2/3. The total ground state energy is U is 3/5 n e to the sub f. Okay, the pressure P is negative partial U with respect to V, du dV partial at constant n. And since E sub f is proportional to n to the 2/3 is proportional to V to the negative 2/3, we could say that U is proportional to V to the negative 2/3. Therefore, P is equal to 2/5 n e to the P is equal to 2/5 n e to the E sub f. And electron degeneracy pressure stabilizes white dwarfs because electrons resist being compressed into already filled quantum states. So that's a condensed version of these answers. And let's just expand upon part A, this derivation of the Fermi energy at zero temperature. Okay, this is interesting, especially if you like this more in detail explanations. Okay, so 4 spin 1/2 fermions, each case state holds 2 particles, the number of states inside the Fermi sphere. N equals 2 times V over 2 pi quantity to the third times 4 pi k sub f cubed over 3. N equals V k sub f cubed over 3 pi squared. So therefore n equals capital N over V equals k sub f cubed over 3 pi squared. So k sub f equals quantity 3 pi squared n raised to the 1/3. The Fermi energy E sub f equals h bar squared k sub f squared over 2m. So E sub f equals h bar squared over 2m, sorry about that, times 3 pi squared n raised to the 2/3. Okay, so now we go to our total energy here. U is now 2 times V over 2 pi quantity cubed, and then we have the integral from 0 to k sub f, h bar squared k squared over 2m 4 pi k squared dk, and then U equals V over pi squared h bar squared over 2m, and then this integral 0 to k sub f, integrating k to the fourth dk. So here U equals V over pi squared h bar squared over 2m k sub f to the 5th over 5. So now we're going to use n equals V k sub f cubed over 3 pi squared. So k sub f to the 5th equals k sub f squared times k sub f cubed. So that's going to equal k sub f squared times the quantity 3 pi squared n over V. So substituting here, U equals V over pi squared h bar squared over 2m times 1/5 k sub f squared times the quantity 3 pi squared n over V. U equals 3/5 n times the quantity h bar squared k sub f squared over 2m. So U equals 3/5 n e sub f. Our pressure here, P equals that negative partial derivative, that du dv partial, evaluated at n. And since E sub f is proportional to n to the 2/3, times that quantity n over v to the 2/3. Then we could say u equals 3/5 n e sub f is proportional to v to the negative 2/3. Okay, so p equals that negative partial derivative du dv. That equals 2/3 u over v. So p is going to equal 2/3 times 1/5 times 3/5 n e sub f. So p is equal to 2/5 n e sub f. Okay, so that's number 7. Now we could move along to, we can move along to number 8. Okay. Whoops, sorry. Okay, number 8, a hydrogen-like atom is subjected to the perturbation H prime equals lambda r squared. Write the first order correction to the energy levels. Part B, evaluate the correction for the 1s state. Part C, discuss how the correction scales with nuclear charge Z. And D, explain why degeneracy complicates perturbation theory for excited states. So this is a time-independent perturbation theory problem. Okay, so here perturbation H prime is equal to this lambda r squared, the first order correction here. We're given this NLM absolute value, NLM lambda r squared, NLM and ket NLM. Technically, I should have said NLM bra lambda r squared, ket NLM, hard to pronounce. So here, what we have for our first order correction to the energy levels, we get that pi, r squared, and L. I'm not pi, what am I saying? Lambda, right? And then we have that expectation value here, r squared, and L. And for hydrogen, 1s state, that size of 1s equals 1 over square root of pi, z over, times the quantity z over a naught to the 3/2 e to the negative zr over a naught. So a standard integral is going to give this, that expectation value r squared in one state equals 3 a naught squared over z squared. Therefore, our E1s first order equals 3 lambda a naught squared over z squared. The correction decreases as z to the negative 2. Excited hydrogenic states are degenerate, so one must diagonalize the perturbation inside the degenerate subspace instead of applying the non-degenerate formula directly. Okay, so that's number 8. We can move along to number 9, and pardon me if I mispronounced anything. Okay, so that's that one here. Moving along to number 9. Okay, consider a trial wave function. Psi of r is a e to the negative alpha r for a particle with Coulomb potential v of r is equal to negative v squared over 4 pi epsilon naught r. I'll read through A through D. Normalize the wave function. Compute the expectation value of the Hamiltonian. Determine the optimal variation parameter alpha, and D, discuss why the variational method is useful for molecular systems where exact solutions are unavailable. Okay, so let's see what we can do with this. Variational method of molecular binding. So trial wave function psi of r equals a e to the negative alpha r. We want to normalize this, setting it equal to 1. 1 equals this magnitude psi squared d cubed r equals 4 pi a squared, integrated from 0 to infinity of this r squared e to the negative 2 alpha r dr. So if we use 0 to infinity r squared e to the negative 2 alpha r dr equals 1 over 4 alpha cubed, we could say that 1 equals pi a squared over alpha cubed. So our a is going to equal quantity alpha cubed over pi to the 1/2. And again, I'm just going through this very quickly. Some intermediary steps have been overlooked. The expectation value of the Coulomb potential is negative E squared over 4 pi epsilon naught times alpha. So E of alpha equals h bar squared alpha squared over 2m minus E squared over 4 pi epsilon naught alpha. If we minimize this dE d alpha equals h bar squared alpha over m minus E squared over 4 pi epsilon naught equals 0. So alpha equals me squared over 4 pi epsilon naught h bar squared. That equals 1 over a naught. So the minimum energy is E sub min equals negative me to the fourth over 2 times the quantity 4 pi epsilon naught squared times h bar squared. And this is exactly the hydrogen ground state energy because the chosen trial function has the exact hydrogenic form. Okay, so that's for number 9. Now we can move along to number 10. Okay, so for number 10, let's see. All right, so electrons move in a weak periodic potential. V of x equals V sub g e to the I gx plus V sub negative g e to the negative I gx. I'll read through these A, B, C, D. Using perturbation theory, derive the energy gap near the Brion zone boundary. Explain the origin of band gaps. Discuss why insulators possess filled bands while metals conduct. In D, describe qualitatively how semiconductor doping alters the Fermi level. So I'm going to go over this in condensed fashion. So nearly free electrons in band structure. Near a Brion zone boundary, and pardon my pronunciations. I know I'm not the best at pronunciations if I mispronounce anything. K is about G over 2. The free electron states that K ket and that K minus G ket become degenerate. Perturbation couples them through V sub G, and the matrix is with those components E naught, V sub G in that first row, second row, V sub G star, E naught. Its eigenvalues are A plus or minus equals E naught plus or minus magnitude of V sub G. Therefore, the band gap is delta E equals 2 times the magnitude of V sub G. Okay, and now band gaps form because Bragg reflection mixes forward and backward moving electron waves at the zone boundary. Okay, insulators have filled bonds separated from empty bonds by a large gap. Metals conduct because they have partially filled bands or overlapping bands. I should have said bands. Okay, sorry about that. Have filled bands separated from empty bands by a large gap. Metals conduct because they have partially filled bands or overlapping bands. My apologies there. Doping a semiconductor shifts the Fermi level. Donor impurities push it upward toward the conduction band, while acceptor impurities pull it downward toward the valence band. Okay, so that takes care of number 10. Number 11. Okay, so number 11. So consider a one-dimensional lattice with a spacing A. Using the tight binding approximation, derive the dispersion relation given here. E of k is equal to E naught minus 2t cos of Ka. Determine the effective mass near Ke. K equals 0. Explain the physical meaning of the hopping parameter T. Discuss how the bandwidth changes as atomic overlap increases. And this is a condensed version of the explanation, so we'll get through it quickly here. So assume localized orbitals with nearest neighbor hopping T. Here we're given the state is going to be that psi sub k equals this sum over n of e to the I k n a phi of x minus na. Our nearest neighbor hopping gives E of k is E naught minus t times the quantity E to the IKA plus e to the negative IKA. So E of k equals E naught minus 2t cosine Ka. Near k equals 0, cosine of ka is about 1 minus k squared a squared over 2. So e of k equals e naught minus 2t plus 2k squared a squared. Compare with e of k, that approximates e sub min plus h bar squared k squared over 2m star. So h bar squared over 2m star, that's equal to ta squared. So m star equals h bar squared over 2ta squared. And rounding this up for 11, the hopping parameter t measures the amplitude for an electron to move between neighboring sites. If orbital overlap increases, t increases, so the bandwidth for t also increases. Okay, so that takes care of number 11. Moving along to number 12. Okay, so number 12. Okay, so I'm going to go through A, B, C, and D first in a condensed fashion, and then we'll go over the derivation of the Larmor precession frequency more in detail on the next page. So a spin 1/2 particle is placed in a magnetic field. B is B naught, Z hat. Okay, B, C, D. Write the Hamiltonian and determine the energy eigenvalues. Derive the Larmor precession frequency. If a transverse oscillating field is applied, explain the condition for resonance. Discuss the physical basis of nuclear magnetic resonance, NMR. Spin in magnetic resonance problem. So, going through this in a condensed fashion, for a spin 1/2 particle in B equals B naught Z hat, the Hamiltonian is H equals negative mu dotted with B. Using mu equals gamma S, we get H equals negative gamma B naught S sub Z. And just so, I'm sorry, and since here we have this, these are equal to each other, these cats, M sub S equals plus or minus 1/2. The energies are going to be E plus or minus equals this following expression. Okay, this minus or plus gamma H bar B naught over 2. And just to add on to this, if we do all the math, we get the E sub M sub S, the eigenvalues equal negative gamma B naught M sub S H bar. Sign convention depends on definition of gamma. Important to note that. Okay, the energy splitting is delta E equals H bar magnitude gamma times B naught. So the Larmor angular frequency is omega sub L equals magnitude gamma times B naught. Resonance occurs when the transverse oscillating field is going to satisfy omega equals omega sub L. And in NMR, nuclei absorb electromagnetic radiation when the radiation frequency matches the spin splitting caused by the external magnetic field. Okay, so just going over that derivation. Okay. Okay, so the spin 1/2 in a magnetic field, use the convention mu equals gamma S, then H equals the dot product of negative mu and B, and for B equals B naught, say Z hat. Well, we also have H equals negative gamma B naught S sub Z. So the spin states obey the following with M sub S equals plus or minus 1/2. We're going to apply the Hamiltonians given here and here. So when we do that, thus E sub ms is going to equal that negative gamma B naught M sub S H bar, and for M sub S that equals plus 1/2. So E plus equals negative gamma H bar B naught over 2, and E minus equals gamma H bar B naught over 2. This is for M sub. So this quantity is for M sub S is 1/2 plus 1/2, and for M sub S negative 1/2, this is that quantity that we get. Okay, so So splitting is delta E equals magnitude of this, and then delta E is going to be equal to the magnitude when we substitute these two quantities here and here. So that's going to wind up yielding delta E is h bar times magnitude of gamma times b naught. Resonance occurs when h bar omega equals delta E. Therefore, omega sub L is gamma, absolute value or magnitude gamma times b naught. And for an electron, it is sometimes expressed as the following: mu equals that gamma s, and which reverses the ordering of E sub plus and E minus, but the physical splitting remains delta E equals h bar magnitude gamma times b naught. Okay. Oh, and that was looks like a minus. Sorry about that. Thank you so much. Hopefully this helps if you're getting ready for a quantum physics of matter exam. Hopefully these problems could be used as just extra practice. And I apologize for mispronouncing anything or going too fast, but hopefully you can use this as a reference. And thank you for watching, and have a great day.